So, welcome back. In the previous lecture, we looked at things called one-forms, which are just elements of the dual space of the tangent space to a manifold at a point. So, if you recall, we have everywhere on a manifold, a smooth differentiable manifold. At every point on our manifold M, we have a vector space Tp of M. That's the space of tangent vectors to P. And in the previous lecture, we introduced another vector space. Which is just the space of functions on this vector space Tp of M. So we have these two vector spaces associated to every point of a manifold. And in the previous lecture, we also introduced a basis for this vector space here. Via these coordinate functions x alpha. All right, so we have this vector space, we have that vector space. We could just go ahead and work with these objects, but it turns out that if we want to build a sensible notion of integration on a manifold, we want to build bigger vector spaces. And these bigger vector spaces will help us build integrals over, or higher dimensional integrals over this manifold M. So our goal in this lecture is to build bigger vector spaces, and this will lead to something called tensor fields, or fields of tensors on our manifold M. So we're going to do that presently, but before I do so, I just want to make one comment about the definition of a one-form and this basis here, and how does this basis transform if you change the coordinate chart that you use to define the one-form. In order to do that, I'll just define some notation that we used in the previous lecture without formally introducing it. We're going to define first a pairing written like an inner product symbol. What does it do? Well, it takes an element of the dual vector space, tangent space there, the cotangent space, and an element of the tangent space, and it gives you a real number. So it eats a cotangent vector and it eats a tangent vector and gives you a number. And what number does it give you? Well, if you go to a coordinate chart, then it's just precisely that number there. And you can check, it's a good exercise, one that I recommend you do, that if you look at this pairing with respect to a different coordinate chart, that this is well defined, this notion is well defined. So it doesn't depend on the coordinate chart you happen to choose. And in order for that to be the case, you have to prove the following exercise. So you have two coordinate charts. And you have some point in their common intersection. And then the task is to prove that the coordinates of your cotangent vector in the new coordinate system are related to those in the old coordinate system via this formula here. So that's a necessary condition in order that this pairing is well defined. So now it's time to actually get into the business of building big vector spaces associated with a point in a differentiable manifold. So we don't have to do that, but we're certainly going to need to do that if we want to build a theory of integration. But it's also very useful, a useful thing in maths and physics, that if you know how to build one thing and another thing, then it's worthwhile thinking about how you put those things together to build even bigger things. So that's our task today. So if you have a vector space and you want to build a bigger vector space from it, you have a couple of operations available to you. So there's two notions of product that make sense on vector spaces. You have the direct sum that takes two vector spaces and gives you a bigger vector space. But you also have another symbol, that's the one we're going to use today, namely the tensor product symbol. And this also takes two vector spaces and builds a bigger vector space. Now we certainly have reasons to take direct sums of tangent spaces at manifolds, but not in the theory we're going to build and use for most of this course. There are other contexts where that makes sense. But for most of this course, that's the way we're going to build bigger vector spaces, we're going to take some vector space V, some vector space W, and we're going to have a bigger vector space as a consequence. So what can we build using the vector spaces that we have available to us via the tensor product symbol? Well, we can build any number of copies of TPM tensored with each other, also tensored with a number of copies of TP star M. That is the space of, that's the set of vector spaces we could build with the tensor product symbol. So we could take some number of copies of TPM and we could say take Q copies, and we could take, we have this other vector space that we've constructed. And we could take R of those, where Q and R are integers, or non-negative numbers. And that would give us a whole swath of new vector spaces to play with associated to a manifold at a point. Some of them will be useful for things to do with integration. Some other things are going to be useful for building vector bundles and blah, 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 which we're not going to cover in this course. But at this point, we're just thinking about what could we build with the toys that we have available to us. What building, with the building blocks we have, how can we stick them together to get new things? We could, of course, take direct sums of these things. We're not going to do that. So an element, if you have some element in that vector space, so an element of such a vector space is called a tensor of type Q, R. It's just a vector, right? So we'll give this vector space a name, Q. What notation shall I use? R, comma, P, let's say. Of M. So this thing, if you just take an element of this huge vector space here, then it's a vector in some vector space. That's all we can say at this point. However, it's not just a vector in a vector space. There's more structure there that we've built in. And that is the multilinear structure of the vector of this vector space here. And we also have a way to extend our pairing between TP and TP star to this vector space here. Extend it by taking a product. So there's a lot more structure in this definition that we should highlight. So we can write our element T in terms of a basis. We have a basis for TPM. We have a basis for TP star M. And when you have a tensor product of vector spaces, you just take the tensor product of the basis vectors, and then you have a basis for the whole vector space. So we can write our element T in terms of a basis of TP and TP star. And what do you get? Well, the most general thing you could find, of course, Q R is this expression here. So this is our basis for the tangent space to the point P. We have this d dx mu. And you just, to get the basis for this, for a tensor product, you just take the tensor product of the basis vectors. It's one basis that will do the job. All right, there you go. That's a general coordinate expression for our element T, our tensor of type . So if our manifold has dimension m, we can wonder how many coefficients do we need to specify one of these tensors. And the answer is, well, you need n to specify a vector in either the tangent or the cotangent space. And if you tensor two vector spaces, you have the number of basis vectors grows quadratically. So the number of coefficients T mu blah 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 nu blah 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 is equal to n to the power q, right? We got n times n all the way up to n coefficients there, times by n times n times n all the way to the nu r. So we need that many coefficients to specify a tensor of type QR. And one final thing that I'll note about just general tensors of type Q and R is that there's a natural pairing between this vector space and the dual of this vector space, where you put the stars here. Via this pairing extended naturally. So what does extended naturally mean? Well, whenever anyone says natural in any branch of science, usually means in the eye of the beholder. So you have to kind of work out what they thought was natural. In this case, the action on a product element of this vector space here will be defined as follows. So Q tensor V1 all the way up to VR. So suppose you have this vector here inside that vector space there. So that's a legal element inside this vector space. It's not the most general element, right? The most general element is a linear combination of products of this form, but it is a vector in that vector space. Then we define the natural action of T on that is just equal to taking the products of the actions. So there's an implied sum there because we have a repeated index. Mu1 is summed over mu1 and so on. And these are just the coefficients of the one form omega 1 with respect to the basis d dx mu1. All right, so this is the natural action, and then you extend by linearity. So it's natural because you would hope that somehow if you have a product of things and this behaves like a product, because there's a vector space and these things span this vector space, you just then, to get the full action, you extend linearly that definition. Alrighty, so now we have a playground of things. We can entertain ourselves endlessly with ever more complicated tensors on even the simplest manifolds. So just to define that notation there before we move on. We're just using that notation there for the coefficient of a cotangent vector, and so on. Also, similarly for the tangent vectors. Good. We have a playground of things to play with. But this is only at one point in the manifold. In fact, this is already an extraordinarily complicated place to live. If you go to a one-point manifold and look at its, it doesn't quite work. If you go to one point of an m-dimensional manifold and look at all the vector spaces you can build fantastically huge vector spaces. As the number of tensor components here grows, these vector spaces grow exponentially in their dimension. And in fact, those set of vector spaces at one point of a manifold are sufficiently complicated that you can capture like a large dose of many-body quantum mechanics right there. So you can simulate many-particle quantum mechanics if you like by just looking at very complicated tensors at one point of an n-dimensional manifold. We're not going to do that, but that certainly is one of the one of the reasons why quantum mechanics itself has a symplectic structure, as we'll see later on. But what happens if we extend this object across the manifold? So far we've always been focusing at the tensor at one given point of the manifold. Well, there's a sort of natural way to extend things. Again, natural is in the eye of the beholder, and natural here should mean that it's very smoothly as you change p, right? We want to define an object which, as you vary p, very smoothly. And we're going to call that thing a tensor field. And the space of tensor fields will turn out to be the natural place for us to be building a theory of integration and also all kinds of other fun things. So we know what a vector field is, right? Express it in a coordinate basis and insist that the coordinate functions very smoothly, and we call it a vector field. We're going to denote the set of vector fields on a manifold M with this x, calligraphic x. I am using calligraphic. I like different calligraphic x. Yeah, that's calligraphic x. And similarly, what's a tensor field on a manifold M? Well, it's something where these coefficient functions, these t mu1 through to mu q and nu1 through to nu r's, they vary smoothly across the manifold. QR. QRP. All right, that wasn't so bad. You could diagnose how smooth one of your tensors are if you just go to a coordinate chart, look at those functions t mu1 through to q, nu1 through to r, and check that you can differentiate these functions as many times as you like at every point in the manifold. Of course, we could define tensors which are k times differentiable, and well, we won't do that, but you can imagine how to extend the definition. And tensors that are only continuously varying across the manifold. I've given the set of vector fields a name, namely calligraphic M. The set of tensor fields of type QR. Well, what's that? It's going to be denoted in the sort of hopefully most notationally natural way, namely calligraphic T to the power Q subscript R M. And just an example of this notation at work. The set of 0, 0 tensors, what are they? Well, they're just functions. That's equal to the functions on the manifold. The set of 1, 0 tensors is the set of vectors, calligraphic M. Yeah, that'll do. All right, this set of tensor fields is too big for us. It's too big for what we want to do. We're going to focus now on a subspace of T. It turns out that whenever you take the tensor product of some vector spaces, there are you always get two natural subspaces for free. So this is always worth pointing out. Whenever you have a bunch of vector spaces and you take the tensor product of the same vector space n times, you're going to get some free subspaces, ones that are, in some sense, naturally canonically defined subspaces. And those consist of the symmetric tensors and the antisymmetric tensors. The ones that when you exchange these tensor factors, because you can identify v tensor v tensor v with any permutation of v tensor v tensor v, you get a natural action of this symmetric group on elements in this vector space, and then you can look at how these elements behave under exchange. So there's a natural action of this thing called the symmetric group on n copies of a vector space. So the symmetric group consists of all permutations, which I've written. I mean, there's multiple notations you can use for permutations. Here's one, here's another, just saying it's a permutation. The symmetric group is a set of all permutations of the set 1, 2, 3, all the way up to n. And there's a natural way that that symmetric group acts on this tensor product here. So I'm going to be slightly not careful in my notation here. I'm going to take pi to act on take the symbol pi both for the representation of the thing and the thing itself. It's a bit sort of naughty, but it should be relatively clear in this context. So it acts or works via its action on product vectors. So you take some product vectors here in that vector space, and pi on that is the new product vector and then you extend by linearity because these they're a linearly independent set of vectors. So this symmetric group acts very nicely on copies of vector spaces. And in this huge collection of vector spaces here, we have examples of this, copies of the same vector space n times. And it's natural, you know, if you have something that acts on a set, it's natural to ask about things that are invariant under that action, things that don't change when you permute things. So we're going to look at the eigenspaces of pi. Look at the eigenspaces of pi corresponding to eigenvalues with plus and minus 1. They'll form subspaces of V tensor V, blah, blah, blah. So the symmetric ones, which we won't spend very much time on, that's the set of vectors in V tensor v, tensor v, tensor v, which are left invariant under the action of permutations. So we're not going to spend much time talking about this very interesting space. It will reappear when you go to advanced quantum mechanics. That is the building block of the Fock space for bosons, bosonic Fock space. And it turns up in a vast variety of places in mathematics. Instead, we're going to focus on the anti-symmetric guys. That's the set of vectors, v, which change up to a possible -1 sign under the action of permutations. So this SGN means the completely anti-symmetric symbol. It just counts the number of transpositions that you need to write a permutation pi. So a transposition is a swap of just two elements. So that's a transposition there. A permutation which takes 1 to 1, 2 to 2, so on, j to k and k to j. Just swaps j and k, and then leaves the others alone. That's a transposition. We call that, I guess we'll call that today tau jk. Turns out any element of the symmetric group can be written as a product of transpositions. So pi can always be written as a product of a jl, kl. It's not a pi, that's a product symbol. And the anti-symmetric symbol just counts the number of transpositions when you write pi as a product of transpositions. And then you might wonder, well, does it not depend on the way I represent my permutation as a product of transpositions? Well, it turns out it's well defined. It doesn't matter. This number is well defined here because the number of transpositions is either odd or even, and that number is well defined, the odd or evenness of the number of transpositions you need to write down a permutation in the symmetric group. And actually, we're done with defining k-forms. So that's a very quick and abstract way to build up the definition of k-forms. I'm going to write it out now a bit more explicitly and slower. But the construction is simply this: take the tensor product of the cotangent vector space k times, restrict to the antisymmetric subspace. That's the definition of a thing called a k-form. That's what I'm going to write out now. You'll see in textbooks more or less tedious definitions of k-forms. For me, this is the most economical way, and it seems the one that has the least moving parts. All right, now we come to our favorite subspace for integration of the set of all tensors, k-forms. Here's our definition. We're defining things called exterior forms of degrees k, or k-forms. While these things, they turn out just to be antisymmetric vectors in our tensor product of cotangent vector space. But here's the version of the definition that you might find more familiar to textbooks. Here's the super tedious way to do it. A k-form is a k-linear antisymmetric function of k vectors. What does the words k-linear antisymmetric mean? Well, it means if you take the linear combination of two vectors and then you take the action of your k-form omega on those vectors, then it behaves linearly but antisymmetric under exchange of the arguments. So it's got to be linear in each entry. It's a k-linear function. And it's got to be antisymmetric, meaning that if we do some permutation of these arguments, we're going to pick up the sign of the permutation that we do. Okay, that was a really tedious way of saying I omega is an element of the antisymmetric vector space. This thing here is called wedge k of v. Oh, k vectors. Where are they coming from? From a vector space V. So if Sim V is what you use to build the Fock space of bosons, then wedge N V is what you use to build the Fock space of fermions. Fermions, you may remember, if you take a fermion in one state and a fermion in another state and you exchange them, you pick up a minus sign. So according to this somewhat strained analogy, K-forms are like fermion. They're like fermions, and we're somehow using this fermionic nature to talk about orientation. The maths is the same, but the applications are wildly different. Now I'll show you a neat trick of how to build these subspaces, sim NV and wedge NV. Okay, wedge KV. So you can work out this vector space here by building the following operator, P minus. P minus is a projection operator. I'll write out what it is exactly. So P minus is action on some vectors V1 through to Vk. Is defined to be 1 on k factorial, the sum over all permutations of k things. Sorry, I made one mistake here. Dual vector space. So you can check that P minus is a projection. And therefore gives you a vector space, and then you can check that it's the same vector space. So that's how you can build omega k of V. Right. And the space of k forms is none other than omega k of V star. Maybe. I'll write it like that. Just here to emphasize that that's what this thing is. Now you have this way of sticking together two vector spaces, right? This standard canonical way of taking two vector spaces to build a bigger vector space, and it's called tensor product. Now, you might hope that something similar exists for these vector spaces here. I mean, they are kind of, they're a subspace of a tensor product vector space. Maybe you can take two spaces of k-forms, stick them together with, say, the tensor product symbol, and get more k-forms. Well, that sort of just about works, and there is a defect, of course. If I take omega k v star and tensor it, just plain old tensor it with omega k v star, then what's left is not completely anisymmetric anymore. It's anisymmetric under the first k tensor factors and under the second k tensor factors, but again, under swapping between the factors, it's symmetric, so that's not quite right, is it? So we want an operation which allows us to build smaller exterior smaller vector spaces of exterior forms, using them to build bigger spaces of exterior forms. And the operation that we're going to introduce is somehow, it's just the tensor product symbol corrected for this defect that it doesn't preserve anti-symmetricity. Here's the definition. So you take some k form omega k and some L form omega L. And you stick them together by defining this thing called this wedge product. And What is it? Well, it's a k plus L form. And the way it works is, well, it should work like the product of these two forms, but corrected to make it completely anisymmetric. So the exterior product of omega k and omega L is this thing here. It's a k plus L form. And the action of omega k wedge omega L on a vector of the form V1 tensor V2 all the way up to k plus L so the action on a vector of this form here is defined by demanding that it basically acts like the product of these two things, but corrected to make it anisymmetric. And that results in this slightly lengthy definition. Okay. There's so many moving parts in this definition here, it's pretty hard to see that it's doing what I'm saying it's doing. Turns out there's a slightly more economical expression for this guy. There's a proportionality factor which I can't remember actually. Although you can work it out very quickly, and that's part of the exercise. So just, so I didn't write it, the exponent k here, but just to tell you on how many factors p minus acts. Actually, I do believe the no. I'm not going to work out the proportionality factor here. That's your exercise. I'll just mess it up, I can see. So this is doing, as advertised, this works much better as a definition. You take some K form, you take some L form, you build its tensor product. Okay, that's canonical. We know how to take tensor products. It's no longer antisymmetric. It's no longer an element of our antisymmetric vector space. Well, what's the simplest thing you could do to make it an element of the antisymmetric vector space? We just project onto that subspace. So you throw out the stuff that isn't antisymmetric.
Excuse me?
Yo.
One question in the definition of the exterior product.
Yes.
Wouldn't there be like every index in a pi? If you know what I mean?
Every index in a pi?
No, like pi of every index on the right side.
Oh, you're wondering why there's not. Yeah. Yeah. So the question is, shouldn't pi be down here? Yes, pi should be down here. Oh yeah, I had it in my notes. I wanted to fit it in the board, you see, that's why I got carried away. All right, let's do it properly. Times by omega L V of pi of k plus 1, blah, 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 V of pi of k plus L. Ugh. All right, that's why this is so much nicer as a definition. So you can see how this corrects things properly. So omega k tensor omega L is an element of omega k V star tensor omega L. V star, that's a subspace of VK, V tensor K, V star tensor K, tensor V star tensor L, right? But this subspace here doesn't intersect perfectly. There's another subspace that we need to be, that we want the wedge product to end up in, and that's wedge K plus L of V star. That's also a subspace of that. It turns out this subspace does not perfectly contain that subspace. There's stuff that goes outside. And in order to restrict yourself to the subspace of these guys that lands in here, well, just project onto that subspace. So that's what the wedge product is doing there. All right, let's check some properties by sending them as an exercise. So prove that this wedge product operation is 1, skew commutative, meaning that if you do omega k wedge omega L, that's equal to -1 to the k times L omega L wedge omega k. Prove that it is distributive. So it distributes over addition. Okay, these two are already pretty straightforward once you know this little result of this exercise here. Like exchanging this tensor factor with that factor is going to pick up a minus sign thanks to this projection operation there. And depending on the dimensions of K and L. And the third exercise is that it's associative. Namely, that if you do it 3 times, it's the same as doing it sequentially. If you do K and L wedge, and then you wedge on an M, that's the same as if you did it the other way around. L, yeah. So associativity is something also very useful. It means you can take brackets out. There's nothing more annoying than non-associative mathematics. You're never allowed to take the brackets out of an expression. Super annoying. But non-associative math is somehow very useful. All right, now I have for you the most important example for all of this course. This is a biggie. We're going to spend pretty much the rest of this course studying and playing around with this one example. Abstracting features of this example, finding generalizations of this example, spotting this example in other examples. This example is the course right now. Example. Suppose we have a vector space, namely Rn. That's the simplest vector space we can write down. Sorry, R2n. That's important. So let V be the vector space R to the 2n, and write coordinates of R to the 2n as tuples P1 through to Pn, semicolon Q1 through to the Qn. It's an even dimensional real vector space. And I've written P's and Q's. When do you see P's and Q's in classical mechanics? That makes you think of momentum and position. This is none other than phase space. We're looking here at phase space. And define the most important exterior form in this course. There it is. Totally innocuous. This is our first symplectic 2 form. And it's the one that captures the area preserving nature of phase space, of Hamiltonian flows on phase space. We'll have a lot more in this course to say about this particular 2 form. Here's a little exercise to get you used to manipulations with these things. Take this two form. Actually, it's not entirely the symplectic two form that will occupy us. I don't know, well, yeah. So the exercise is now take that two form and just wedge it twice, see what comes out. Well, I won't leave you dangling. I'll at least tell you the answer. So that's a good exercise for you. Check that that works. Of course, in order to do that exercise, it's pretty crucial that you've done these ones over here. Because you can see how that property is going to play a role in working out this skew commutativity. It's very important. Also, the distributivity is going to be important, and definitely associativity. So you need all three of those properties to prove that omega 2 wedge omega 2 has this particular form here. All right, I've got two more topics to cover before the end of today. So we have this very lovely vector space of exterior K-forms. Whenever you have a vector space and you have a basis for a vector space, you can work out a basis for the vector space of exterior K-forms. It's very useful to have bases, because if you ever want to do a calculation, you're going to have to put it, and you'll probably have to put it on a computer when it's sufficiently complicated. A basis is the only way to get it into the computer. Computers don't know basis coordinate-free notation. Unless you work really hard. But they sure know about things expressed as in terms of bases. So we need a basis. So let's create a basis now for omega, for the wedge product of a vector space. Basis for wedge KV. There's a little exercise for you. Show that that wedge product, when extended to vector spaces, actually is the same as wedge KV. All right, let's suppose we have a basis EJ of V. Then I'm just going to present to you the basis of wedge KV. Because we've defined this wedge product so well, it's going to be the direct natural categorical extension of the tensor product symbol. So these vectors here are a basis for wedge K of V. And why is that a basis? So I'm going to give you the argument. I'm not going to prove it, but like, if when you note these 2 points, it's basically a proof. Firstly, if you take the same basis vector and wedge it with itself, you get 0. And the reason for that is skew commutativity over here. Pick up a minus sign under X swap, but it's the same vector. So how could this vector equal minus itself? Only when it's 0. And, well, also note that omega j wedge, let's say 1 and 2, is equal to minus omega, I meant E, sorry. Same property, right? Note that if you swap these guys, you get a minus sign. And so if you had these things with indices not in increasing order, you can just swap them around until they're in increasing order, have the same vector up to a plus or minus. And that's why you can restrict these vectors to be have subscripts in increasing order. And that's basically how you prove that that's a basis. Yeah?
Could one also say that these are the image under P minus of a basis of like the tensor?
That's a good question, yes. Are these things the image under P minus of just the tensor product basis?
Like any.
And the answer is yes, absolutely. So P minus either annihilates these basis vectors, tensor product vectors, or it projects them onto these things. So yeah, absolutely. So P minus is a very nice way to build that basis. But there's one sort of thing to warn you about. If you take a tensor product of basis vectors and hit it with P minus, there's a proportionality factor that's a bit wrong. You have to work out a proportionality factor. It's the only thing to be careful about. Yeah. So what's a very beautiful consequence of this? Well, we can work out the dimension of this vector space wedge KV. K choose N choose K. Where N is the dimension of the vector space V. Oh, where am I? Over here. So you can use this basis to write out an element of wedge KV. Well, it's just some linear combination of the basis vectors, so that was easy. And also, it's a pretty quick consequence. Remind yourself of some permutations and so on and counting problems, and you should convince yourself that the dimension of our wedge KV vector space is N choose K, where our vector space V had dimension N. now we're ready to define the objects we're going to need, namely differential K forms. So these are going to be wedge elements of the wedge product vector space of the set of cotangent vectors. I'll write that out explicitly. So a differential form of order K at some point Q in a manifold M, well, it's just an exterior K form. On the tangent space V. I didn't name it. Omega K. So another way of saying is that omega K is just an element of the K-fold wedge of the dual vector space to V. So what's a differential form of order K at a point Q? Well, it's just an element of this K-fold wedge product of the dual to V, the tangent space. And if it's smoothly varying, smoothly assigned to each point when you write it out in coordinate functions, then you say it's a K form, for short. So it's a tensor field, right? Because it's this vector space here is a subspace of the set of tensors, of K tensors. So a differential form or a K form is a tensor field, but it's a tensor field with extra properties. Namely, it's antisymmetric under exchange. And the final thing I'll write out is the coordinate representation . And then we'll be done. All right, we have this nice basis. For the cotangent space. Then I just wrote out what is the basis of wedge KV. And we have the following theorem as a consequence. right, if you have an arbitrary K-form on the example manifold Rn, then if you have this coordinate system here, this is a global coordinate system, you need one chart to cover Rn, then you can write a K-form in this particular way here in terms of that basis. So I think at this point, it's a good moment to stop. So thank you very much.